This video is on exponential decay. The equation for exponential growth and decay is y equals a times b raised to the exponent of x. This equation is used for both exponential growth and decay. The a is your initial value, which means it's your starting amount. Because the a is not being raised to the exponent of x. This would be considered your y-intercept. Your b value is your growth or decay factor. This lets you know if you're dealing with growth or decay. The exponent of x is really important because the x is an exponent. It is not being multiplied. It is not a variable that has a coefficient. X is an exponent, which makes it an exponential instead of a linear equation. So if we're looking at tables, we want to determine as the x's increase, what are the y's doing? You can see that the y's are getting smaller as it moves on. So I could do 6 minus 3 to get 3, but 3 minus 3 does not give me 1.5. So this is not a linear function because I am not decreasing at a constant rate. I am decreasing by multiplying values. So we could probably determine what the value is, but instead of guessing and checking, we can do some simple math. We could take the second y value and divide it by the previous one to determine how we got to it. So we can take the value of 3, the y value of 3, and divide it by the previous of 6. This gives us a 1/2. 3 divided by 6 is 1/2. Then we have 1.5 divided by 3, which will also give us a 1/2. So far this is the same value, so this is a constant multiplicative factor. And then we have the third one of 75 hundredths divided by 1.5 gives us also half. What that tells us is that to get from 6 to 3, we multiply by 1/2. To get from 3 to 1.5, we multiply by 1/2. And to get from 1.5 to 75 hundredths, we multiply by 1/2. So if I wanted to get to the next value, my next value, I would take what I have now and I would multiply it by 1/2 to get to the next y value. I just have to know what I started at. We started at the y value of 6 because that was our y-intercept of 0, 6. So now that we have our next now, we can write our actual exponential equation. Now, since our multiplicative factor is smaller than 1, this is going to be a decay, exponential decay. So we have y equals our starting value, our y-intercept of 0, 6. So we have 6 times, every time we're multiplying by 1/2, raised to the power of x. We could also see this as a decimal of y equals 6 times 5/10 raised to the power of x. And now you can easily see that 0 and 5/10 is smaller than 1. So that tells us that it is in fact a decay factor. It is an exponential decay. So if we look at the second one, we can see as the x's increase, the y's are getting smaller, but not by subtracting the same amount each time. And again, this one might be a little harder to just automatically recognize what's being multiplied. So that's why we use the simple math of taking your y value and dividing it by the previous. So we take the 16 and divide it by 20. We get a decimal. We get 8/10. This is smaller than 1. Then we take the next one of 12 and 8/10 divided by 16, the previous y value, and we get 8/10 as well. The last one is 10 and 24 hundredths divided by 12 and 8/10, and we get 8/10. So all three of these are the same value and they're all smaller than 1. That means that this is decay. So to get from 20 to 16, we would have multiplied by 8/10. To get from 16 to 12 and 8/10, we would have multiplied by 8/10. To get from 12 and 8/10 to 10 and 24/100, we would have multiplied by 8/10. That's how we find our multiplicative factor. If I wanted the y value when x is 4, I would want to get my next value. I would take my 10 and 24/100, what I have now, and I would multiply by 8/10, knowing that I'm starting at the y value of 20. So my exponential decay equation will be y equals, I am starting at 20, and I am multiplying by 8/10 each time. And so it's each time, so I'm raising it to the exponent of x. On this third table, we're going to do the same thing. I'm going to see how the y values change. So I could see that I am subtracting 15, but I won't do the same thing from 5 to 1 and 25/100. That means I'm going to try and divide or multiply by a fraction. So I'll take my second y value and divide it by my first. 5 divided by 20, I'll get a decimal, is a quarter, so we're 25/100. Then I'll take 1 and 25/100 and divide that by 5, which does give me 25/100. And then I'll take our last decimal, or our last y value, and divide it by our one previous. And when I divide that, it does give us 25/100. So all three of these are the same, so I know that we have multiplied by the same amount. And these are all smaller than 1, so this is an exponential decay equation. So to get from 20 to 5, we would multiply by a quarter. To get from 5 to 1 and 25/100, we would multiply by a quarter. And for this last one, we would multiply by a quarter. So to get from 1 and 25/100 to 0.3125, we would multiply by a quarter. So again, to get our next value, which would be at the x value of 4, we would take our last value, what we have now, and we would multiply it by a quarter, as long as we know we're starting at 20. So our equation would be y equals, we started at 20, and we're multiplying each time by a quarter, so we raise that to the exponent of x, because we're multiplying it each time. So what do the numbers actually mean in the rule? We have the 32 and the 35/100. So the 32, we know, is our starting value. It's the starting amount. Because this value is not being raised to the exponent. So the 32 is kind of all by itself. This would be your y-intercept, so it would be 0, 32. The 35/100 is your it's telling us that this is decay. This is decreasing. It decreased by a factor. This is your decay factor of 35/100, because that's what we're multiplying by 35/100 each time. That's why it's the decay factor, because that's what we're multiplying by. This is different than the decay rate. We're going to talk about the decay rate, just like growth rate. Decay rate is completely different than decay factor. The factor is the actual number in here. The decay rate is a percentage. Right now we have 35/100 is the same thing as saying 35%, because it's 35 out of 100. 35% is away from 100%. That's what we want to figure out. How far away is 35 away from 100. So 35% is 65% away from 100%. We have to take how far away is 35 from 100. So if we take 100, take away the 35, we're left with 65. That tells us that our decay rate is 65%, because it's how far away your factor is from 1, or your percent is from 100%. You don't see this number in the equation because we have to determine how far the percent is away from 100%. That's the difference between the factor. Factor is the number we see because that's what we're multiplying each time. The rate is the percentage that it is decreasing by each time.